Hello students, in this video we'll discuss the beta of an asset with respect to a portfolio. Let's consider a collection of stocks on the minimal variance line. These are the stocks that have the maximum return with the smallest variance. If we plot these stocks on the risk return axis, we saw previously that they will form the efficient frontier, which is a hyperbola. If in addition to points on this efficient frontier, we have a bond with no risk and a risk-free rate of return R, if we connect the bond to the efficient frontier on a line, this line will intersect the efficient frontier at a point that has risk sigma m, Rm, and this line is the capital asset line. Suppose now that we choose another stock, sigma 1, R1, and we can form the hyperbola which goes to the point sigma 1, R1 and sigma m, Rm, and it will also be tangent to the capital asset line. So the portfolios which contain the market portfolio and the S1 stock with point sigma 1 R1 must form a hyperbola which is also tangent to the capital asset line at the point sigma m Rm. To find the slope of this line, we'll consider the following. So the slope can be found by doing the following calculation. We consider lambda in the direction of the first stock, S1, plus 1 minus lambda in the proportion of the market portfolio, M. And so if we look at this in terms of returns, the return will be lambda, the return, R1, plus 1 minus lambda, Rm. And the risk will be the square root of lambda squared sigma 1 squared plus 1 minus lambda squared sigma m squared plus twice lambda 1 minus lambda, and then the covariance of the return K1 and Km. And what we seek to do is we seek to find the slope of the line between these 2 points at lambda equals 0. So we take by differentiating and setting lambda equals 0. So we'll do the derivative of the risk and the derivative of the return. The slope will be the change in the return over the change in the risk. So the slope will be the change in the return at lambda equals 0. Well, the change in the return at lambda equals 0 will simply just be R1 minus Rm. R1 minus Rm. The denominator is substantially more complex. What we can do is we can say that the risk is this entire expression. So we'll call this entire expression over here f of lambda. So it'll be f of lambda to the 1/2 power. And if I do the derivative with respect to lambda, we will see this is 1/2 f of lambda to the negative 1/2 times f prime of lambda. And we can see what happens when we plug in lambda equals 0. If I plug in lambda equals 0, I will get a 1/2. Then I'll have this expression to the negative 1/2 power when I plug in lambda equals 0. So I'll get a sigma m squared. And when I plug in lambda equals 0 over here, I will get nothing. So this will be to the power negative 1/2 times the derivative of this with respect to lambda at lambda equals 0. So this term will vanish. This term will give me a negative 2 sigma m squared. And then when I differentiate this and plug in lambda equals 0, what we will get is we will get a 2 minus 4 lambda. So all that will survive is the 2 covariance of km and k1. So this expression over here is exactly the slope of the line. We can now observe that what will happen is this 1/2 will cancel with a 2 and will cancel with that 2. And so what we have over here is we have R1 minus Rm over, we will have a sigma m times the covariance of k1 and km minus sigma m squared. If we plug this slope into the point slope form of the line, we will see that this line and the capital asset line will coincide, and this allows me to define the beta value, which is the slope of this line, and the beta value which we'll define is the covariance of k1 and km over the variance of km, which represents the slope of the line we found between the point sigma m rm and the tangent line to this capital asset line. In further videos, we'll see properties of this beta, but one thing that's immediate from this is that since the covariance is linear in either of the slots, this expression is linear in K1. We'll see how this helps us in later videos. Thank you very much.